I loved math growing up. It was my favorite subject. I eventually got into science around high school, but I've always loved math, which is part of the reason I ended up becoming a physical chemist. For the longest time, I thought I wanted to be a math professor. And then I thought I wanted to be a chemical engineer, something that combined chemistry and math and physics. And so in the end, I went for chemistry professor and in physical chemistry, which also combines chemistry, math, and physics. So.
Hello everyone, welcome to another interview of the series of interviews conducted by Department of Chemistry, University of Colombo. We are conducting these interviews to seek the life journey of eminent scientists and what aspects of their journey made what they are today, which will be a massive influence on young scientists. I am Manisha Gunawardana, and here we have Harshika Dissanayaka and Gayatri Dhananjana joined with us. We all are fourth year undergraduates of Department of Chemistry, University of Colombo. Over to you, Harshika.
Today, we are here with an eminent scientist, Professor Christine Aikens, who is a distinguished professor of physical chemistry in the Department of Chemistry at the Kansas State University, United States. She graduated from University of Oklahoma with a bachelor's degree in chemistry in 2000. She completed her doctoral degree in physical chemistry from Iowa State University in 2005. And she served as a postdoctoral research fellow at Northwestern University. Eventually, she joined Kansas State University in 2007. She has published more than 110 articles in scientific publications. And she has also served as a reviewer for 37 journals. She has many achievements in her journey for her remarkable research works. Among those, I would like to mention few. She received Sedgwick Distinguished Faculty Achievement Awards in 2014 and Women Chemist Committee Rising Star Award in 2020. And very recently, she was bestowed the title of University Distinguished Professor, which is the highest honor that Kansas State University bestows on its faculty members. Over to you, Gayatri.
So, without further delay, let's move to our program. Good morning, Professor Christine Aikens.
Good morning.
I warmly welcome you to the interview, and it is truly a privilege and an honor to be able to do this interview with you. Thank you very much for joining us.
Well, thank you very much. It's an honor to be asked. So thank you.
To begin with, would you mind giving us a brief introduction about yourself, your childhood, early education, and also family background?
Sure. So I grew up in Boise, Idaho, which is in the northwest part of the United States. I grew up in a family with 3 younger brothers, so fairly large family. And we always, I think the whole family generally liked math and science. I loved math growing up. It was my favorite subject. I eventually got into science around high school, but I've always loved math, which is part of the reason I ended up becoming a physical chemist. For the longest time, I thought I wanted to be a math professor. And then I thought I wanted to be a chemical engineer, something that combined chemistry and math and physics. And so in the end, I went for chemistry professor and in physical chemistry, which also combines chemistry, math, and physics. So I knew what I wanted to do, just kind of figured out exactly where it wanted to be. So I've changed to chemistry major during college and decided I wanted to do physical chemistry and research. So decided to go for a PhD at that point.
That's interesting, Professor. So, Professor, when did you fall in love for science? Was there any particular reason for choosing this pathway?
Right. Well, like I said, I've always loved math, and I was always interested in science. So I explored a number of things during high school, and I remember enjoying chemistry in high school and thinking that would be a fun area to go into. By that point, I'd heard that it wasn't necessarily practical to study math, I think that's wrong. I think there actually are a lot of practical things one can do with just math as well. But so I was looking for things like science, and chemistry was really interesting. So I proceeded with that. So I can't think of any one particular thing that got me interested in science, but of course I had a number of interesting science professors, and it's just always seemed like a natural fit for me.
So it seems you are passionate about science. So how was the influence of your PhD to what you are doing today? And how was your postgraduate studies?
Yeah, so certainly PhD had a huge influence on what I decided to study. I had done some undergrad research and decided I really liked electronic structure theory, so studying quantum mechanics and chemistry. And so that's what I decided to do for PhD. So I went to Iowa State, where I worked with Mark Gordon. Mark was a wonderful person to work with. He was somebody who cared about a person not only as a scientist, but also as a person. And I think that's really important. So, in general, I encourage people when they're looking for a PhD to find an advisor who cares about you as a person, in addition to a scientist. He had this ability to kind of know where students were. And so if you needed more hands-on work, he would work with you more hands-on. If you were able to be independent, he would allow you to be more independent, and therefore you could develop the skills independently. And of course, as you go through PhD, that's one of the things you're trying to develop, is more and more independence. So with my PhD, I think it really gave me a very strong background in the fundamentals of quantum chemistry. So taking classes and just doing the research, but just kind of understanding all the things that we think of as basic quantum chemistry techniques to do an energy calculation, to do a geometry optimization calculation, to do a frequency calculation, to add in solvation effects. How do we extrapolate from small basis set to large basis set, or from a low level method to a higher level method? How do we get the right answer for the right reasons? That's certainly a phrase we use a lot in electronic structure theory, is getting the right answer for the right reasons. And so all of those sorts of things I got to learn as a PhD student. And then when I went to postdoc, I would say that one of the emphases that George Schatz had was on really trying to connect in with experiment. And I learned that theoretical chemistry was not just electronic structure theory or just classical molecular dynamics, but there was quite a breadth of additional things outside of those two areas that I normally thought of as theoretical chemistry. So for example, he did some classical electrodynamics work. I stayed with the quantum chemistry, but started to work with metal nanoparticles and found that those were quite interesting to me. I loved the spectroscopy. I loved thinking about electrons. I loved, the nanoparticles, just the various different aspects of those systems. So definitely had a big influence.
That's great, Professor. So let's move to the significant part of our interview. As you are mainly working on nanoclusters of noble metals, can you explain the major differences you observe between nanoclusters and nanoparticles?
Certainly. So nanoparticles is a pretty general term, and it can cover things that have at least one dimension on the nanoscale. Now, lots of times when somebody refers to a nanoparticle, it may be something that's not particularly well defined. It may be fairly large. It might range from 10,000 to 12,000 atoms, or it might range from 10,000 to 11,000 atoms, or 10,000 to, but there's usually a range. Lots of times when we refer to nanoclusters, we're talking about something that's fairly small. It's maybe 1, 2, maybe 3 nanometers, but usually about 1 or 2 nanometers in size. And oftentimes it's atomically precise. So you could take a mass spec of the cluster and you would know how many metal atoms are there, how many ligands are there. And so it doesn't have to be atomically precise. We may or may not know that information about the system to call it a nanocluster, but lots of times these nanoclusters are atomically precise clusters. And that's helpful then because we can really identify properties and associate properties with that particular stoichiometry. And each particular stoichiometry may have one or maybe a couple of isomers, but typically, you often think of the one lowest energy isomer. So you can start to correlate structure, function, stoichiometry, all of these important aspects of the clusters.
It seems that you are interested in theoretical calculation of gold thiolate nanoparticles. We would like to know what were your major concerns in that project and how far you have progressed.
Sure. So of course, with the gold thiolate particles, we started off looking a lot at optical absorption of these particles and trying to compare with experiment, understand where certain peaks in an optical absorption spectrum would come from, what types of transitions they were, if they were localized inside the core of the nanoparticle, or if they were a transfer from the core to the ligand shell. So what types of transitions were involved in the optical absorption spectrum? We then found that a lot of the nanoparticles were chiral. So the way that the thiolate units pack on the nanoparticle often leads to chirality in the system. Or alternatively, sometimes people will use chiral ligands and therefore definitely have chirality. So there's a lot of chirality in these nanoclusters. And so we started to look at circular dichroism spectrum. So the CD spectrum of a cluster is something that looks at the difference between the right and left-handed polarized light. And so you get a little bit more information. So an optical absorption spectrum can sometimes be fairly flat. Sometimes it's more structured, and a lot of these nanoclusters have a lot of peaks, but sometimes they're fairly flat. But a circular dichroism spectrum will have positive and negative signals, and so it's a little bit easier to correlate experimental spectrum, a theoretical spectrum. You can really see that there are a lot of states that are causing it in the spectrum. So those were a couple of things we did. We've expanded to a number of other techniques like magnetic circular dichroism, where even if you have an achiral cluster, if you apply a magnetic field, you can potentially induce this same kind of getting positive and negative signals. But then one of the areas we've been focusing a lot on lately has been luminescence. We're really trying to understand how these clusters, once they absorb emission, how that energy relaxes until we get to, say, the emissive state, and then understand this emission. Because some of the clusters that we work with, they're very emissive. Other clusters are not very emissive. And so trying to understand what makes a cluster really emissive as opposed to one that's not emissive is one of the things that we're very interested in at the moment. Now, luminescence in general, there are a lot of complications with that, because we do need to think about how the electrons get excited into those excited states, and then how those relax. So we usually have to use non-adiabatic methods. Lots of times it's non-adiabatic dynamics types of techniques. So we can look at, if we get excited into the 6th excited state, how does it transfer to the 5th, 4th, 3rd, 2nd, 1st excited state before it's likely to emit. And we know that the faster that procedure goes, we can correlate basically the speed of that procedure with certain techniques like transient absorption techniques that are done experimentally. And then the luminescence also has a lifetime, because you can stay in that excited state that's emitting for a while. And so how long can you stay in there? Is it a singlet or a triplet state that's emitting? We've been trying to figure that one out. It's got a fairly long lifetime, most of these states, and so that often means a triplet state. But we're also seeing that many times these states are symmetry forbidden, and that's causing a long lifetime. And so there could be two different factors there that are causing these to often have a very long luminescence lifetime. It's an area where there's, I think, a lot that one could do both in terms of just the fundamental physical understanding of the system. Also, it's a fairly computationally intensive type of calculation. It can take us a really long time. So for example, one of my students is trying to work on a more efficient method to do some of the excited state optimization work, so that we can do that a little bit faster. Because otherwise some of our luminescence calculations can take us a couple of months to do. And we'd really like to get that down to a week or two. It'd be a lot nicer. So we're working a little bit on method development in that area. Another area that I think is a challenge, future challenge, is the idea of dynamics and trying to think about how the nanoparticles move in general and what do we do for the dynamics there. I think there are a lot of areas one can go forward with in this gold thiolate nanoparticle research if anybody is interested.
That's very informative, Professor. So you and your research group are involved in investigating surface plasmon resonance of nanoclusters. Can you explain the fundamentals of that?
Well, sure. So a metal nanoparticle, we're typically dealing with something like silver or gold, but also aluminum would have similar properties as well. These types of metals have some very loosely held electrons. It's typical that we think of metals as having loosely held electrons, but these definitely have loosely held electrons. And so if you imagine you have a nanoparticle and an electric field comes in, so this field's oscillating and it causes the electrons in the metal to slosh up and down. And we think of it as a collective motion that, at least the full electron density is kind of moving up and moving down. Any individual electron may or may not be doing exactly what we think of there, but collectively, we think of all of the electrons basically sloshing up and sloshing down when the electric field comes. And so that's really the fundamentals of the plasmon resonance. It's very much affected by the shape of the nanoparticle. So symmetry and all the boundary conditions that you get from symmetry really affect how an absorption shows up, if we're dealing with absorption. So it's just, very much affected by shape, by size, by composition, if it's gold, if it's silver, if it's a mixture of the two. Many factors that go into that plasmon resonance.
It's really important to us. Professor, in your point of view, what will be the future of nanocluster field? Then what are the possible research areas and opportunities emerging that scientists can work on?
Sure. So I think that a couple of areas where a lot of work will be done in the near future, and so great places for interested students to start to think about. One would be the dynamics aspect. So we can work a lot with a static nanoparticle. We can try to understand its properties, but of course we know in experiment, we don't have just a static structure for this nanoparticle. It's really moving around. It's interacting with the solvent. And so to really treat those, dynamical properties, we need to do some sort of dynamics. We need to see how things are moving with time. Well, the question becomes, how do we do that dynamics? We might do density functional theory, but that's really time consuming. So we're not going to get a very long trajectory for our dynamics if we do everything with density functional theory. There's still some use to that, but we are limited in time. And so there are certain things you can't do. Like you can't necessarily have enough time for one nanoparticle and another nanoparticle to come together and react if you're doing density functional theory. So some people try to do classical force fields, but one of the problems with classical force fields is that you can't do reactions. We'd like to do reactions. There are some things called reactive force fields. They're extremely time consuming to parameterize. Even the classical force fields, there are a lot of parameters that are still needed if you're going to do gold thiolate nanoparticles. There have been a couple of force fields lately that have been pretty good for dealing with these nanoparticles, but then they perhaps don't have some of the interactions with oxygen yet built in. And so there would be a lot of effort I think, towards developing better force fields in the classical MD, there's definitely a lot of space for studying the reactive force fields. And then there are other newer approaches too. For example, some people are trying to use machine learning. So the idea would be that you'd take DFT dynamics for a while, and then you'd study different descriptors and how those descriptors perhaps change, are related to changes in energy or changes in the gradients, the forces that are experienced by the nanoparticle. And then the idea is that the computer is going to determine the correlations, and then it can predict for other structures what that energy would be. And so it will just do a series of very fast matrix multiplies instead of doing the very complicated DFT for each step. But the idea is that the machine would have learned essentially what DFT would say about a particular structure and give it that energy. So I think there are a lot of areas that people could do. So that's certainly one particular challenge. Another challenge, I think, is still better description of non-adiabatic effects. We're having to do a number of different approximations when we treat the non-adiabatic effects. And so one can always start to say, okay, which approximations are good? Which approximations should we scale back on? Are there other different approximations that we could add that would lead to good accuracy, but greatly speed up the computational time? So I think there are a lot of directions that one could go.
With that, let's move on to another segment of your interesting work. You have worked on developing water splitting catalysts from cobalt models. How are the cobalt catalysts being used in water splitting? How have you developed it?
So it's an area that we had worked on for a while. We haven't done anything with this lately. We had been working on the cobalt catalyst because, as you probably know, they're of interest experimentally as water splitting catalysts. So we've done some work trying to understand things like spin states, how the spin states can change in the course of the reaction, but oftentimes we want to think about spin states staying the same, but we really wanted to be careful thinking about spin states. One of the things we learned when we were dealing with this cobalt catalyst is that, again, I think dynamics is very important. We can study a static structure, and we can spend a lot of time studying that static structure. But especially when you're dealing with water, water is constantly moving, interacting. Those hydrogen bonds are breaking, forming. It really affects this water splitting process. And so, although we can learn some things from a static structure, I think we really need to move beyond the static structure and think about dynamics and really think about explicit interactions with the water molecules and how that works during the water splitting process. Again, that brings up all the issues with dynamics that I mentioned before. How does one do this in an accurate way, but do it fast enough that you can get reasonable results from that? And so I think that's definitely a challenge in the field.
So, Professor, not only that, but also you have worked on developing a sustainable world through biorenewable materials. What are your thoughts on that? How far you have come in the road of sustainability?
Yeah, so we were doing a number of things, trying to look at some interactions with polymers, with magnesium oxide, for instance. So our group was studying the very fundamental interactions, trying to look at just the surface interaction between the metal oxide and different molecules. And so we learned certainly some things, and then we had some experimental collaborators at the time that were working on studying the different polymers that could form from this work. It's an area that I'd love to do more in. We don't currently have a lot going on in that direction, but of course it's so important for sustainability. So.
Professor, as you have involved in many research activities in variety of areas, we would like to know your most favorite one out of them.
Okay. Well, certainly I love the luminescence because it allows me to do the spectra, to look at excited states, to think about, these really dense excited states. There are many, many excited states within a very small energy range. I've always loved metals, and I think they're just really fascinating to work with. And then, of course, that brings in some of the issues of non-adiabatic effects and even allows us the melt method development area. So it really lets us put a lot of things together. But I just find it to be a fascinating field. Another one that I haven't mentioned, but it's been a really interesting thing lately, has been looking at nonlinear excitation in these metal nanoclusters. So what we've been doing is doing some real-time, time-dependent density functional theory, which allows us essentially to look at how the electron density changes in time. And it turns out that if you're exciting some of these metal nanoparticles, you start with this initial excitation, this sloshing of this plasmon, but eventually that plasmon essentially interacts with itself and starts to lead to double excitations or triple excitations within the nanoparticle, which maybe doesn't have this strong dipolar nature. So, initially we had this dipolar nature where it's going back and forth, but you can start to get quadrupolar nature, and just these higher energy excitations start to occur within the nanoparticle. And it's been known for a while that these nanoparticles can have nonlinear excitation, but it's been, I think, the first time we've been able to really see it happen in real time. And so that was really exciting when we got to see that.
Professor, it's very fascinating. With that, new discoveries of science in one field will open the gates for a number of other fields. Professor, how these groundbreaking discoveries have spread in other areas?
Okay. Well, I would say, our work probably on optical absorption and circular dichroism has been what's spread the most. So we had started doing some optical absorption on these nanoclusters, and now it's a pretty well-established technique, and a lot of groups are doing that. We were also the first to look at circular dichroism in those nanoclusters and start to think about it. And a number of other groups have started to apply that as well. And so I guess there were a couple studies, but yeah, we were one of the first to do a lot of studies on the nanoclusters. So there's been a lot of spread in terms of how many groups are doing the circular dichroism calculations. So I think that those are definitely ones where we can feel like we've made a contribution to the field.
Next, Professor, I would like to ask this general question. In this decade, there have been a tremendous development in nanomaterials along with the supramolecular chemistry. Do you believe one day we could make this world change through this cutting-edge science?
Well, certainly. I think it's hard to predict exactly where the field's going to go because it changes so rapidly. But we now have nanomaterials that are good for cancer therapy, and they're even being used clinically. It's not just in the tests anymore. So it's amazing to me where things have gone. I think the sky is really the limit. We don't know what they may be useful for, but certainly catalysis is an obvious area where people are very interested in nanoparticles. Building assemblies of these nanoparticles, which would include both the supramolecular and the nanomaterials, is an area where people are looking at trying to build some particular structure that has particular optical properties, because it has not only the optical properties of the individual nanoparticle building block, but then how they're arranged. Because we certainly know that nanoparticles, when they're arranged in certain ways, will have different properties than just the individual nanoparticles. So I think there are so many areas that one could study and so many different possible applications that could come from it.
Professor, you have won many awards. We would like to know the secret behind your achievements.
Yeah. Well, I think it's very important that you find something that you are interested in, because you want to enjoy the work that you're doing. And then you're much more likely to, really thoroughly understand it. I think spending that kind of mental puzzle time to figure out what you're interested in. So, throughout all of that, you're looking to find something that you're interested in, but then you're also paying attention to the field and looking for a little niche where you can fit that nobody else is. If you're working in the field where there are 10,000 researchers working in, it's a little harder to find that particular spot. But if you happen to find a field that's a little more wide open, it's very easy to go in lots of different directions and say, okay, let me go this way, or let me go that way, let me go this way. So don't be afraid to try hard things, new things that nobody's tried before. I know sometimes when you're getting started, you feel like you want to try something that you know is going to work, and that's fine because you're trying to get started. But once you start getting the confidence to explore, I think that's a good thing to do.
Very encouraging, Professor. Based on your experience as a leading scientist, what advice would you like to convey to the young scientists or students who are studying science to succeed?
Sure. Well, again, look and try to find an area that you are passionate about and that you feel like you can make a difference in. So hopefully it combines some of your strengths and expertise with your passion, and that's good to do. And then, when you're in graduate school, for instance, you'll have a lot of opportunity to try new things. And so it's good to try a lot of things, but it's also good to find something that you can really focus on and get to be kind of the expert on. So you'll have some definite depth to that particular area. So I think graduate school is a lot about developing depth in an area so that you become an expert in one particular area. And it'll be a pretty narrow area. It wouldn't even just be physical chemistry, for instance, or just electronic structure theory, but you get kind of narrow, you get it to be an expert in one area. But of course, do be looking at everything else that's around and kind of getting, some experience in new things, because you never know where it'll take your career. You might discover that one of these things that you looked at just briefly is where you really want to do a postdoc in and where you want to take your career in the future or something. So certainly that combination of having some depth and having some breadth is important. And then perseverance, I think, is really important. Lots of times things don't work the first time, and they may not work the 20th time. And so figuring out how you go, okay, I've got a wall here. How do I get beyond this wall? Do I go over the wall? Do I go around the wall? Do I go under the wall? How do I get around this wall? And sometimes you find that this wall is just not going to move, and it's okay to switch a project at that point. But you do want to spend a lot of time trying to figure out how do you get around that wall before just saying, oh, I'm going to do something else. But again, sometimes there are times where you just need to say, okay, this project's not working. I'm going to do a different project. And then, like I said kind of earlier, I would say, make sure you choose an advisor who cares about you and make sure that they know how you're developing. So they're seeing how you develop as a scientist, both in terms of your perseverance and your creativity, but then also knows if the stress is getting to you or anything like that. And so you can address those issues before it becomes a problem, for instance.
The advice you gave is very significant for us. So we have now reached the end of this valuable interview. However, before the end, Professor, is there anything else that you would like to share with us?
Sure. I think that graduate school is a fantastic time if you're looking at graduate school, or it's a wonderful time to explore things, to get to travel, to see, science performed on a different scale and in different environments. It's a fantastic time just to do that kind of exploration. And so you just be as prepared as you can. And sometimes you get really lucky with opportunities that come by. And so just be prepared to jump on those opportunities that come around.
That's really great. This concludes our interview. And Professor, we are truly grateful for the insightful time spent with you. Thank you, Professor Christine Aikens, for spending your precious time and sharing your valuable ideas and knowledge with us.
Well, thank you all very, very much.
Thank you once again, Professor. Wish you the best for every step of your future work. Today, we have interviewed Professor Christine Aikens, who is a distinguished professor of physical chemistry in the Department of Chemistry at the Kansas State University of United States.
Thank you everyone for taking the time to be here today. And I think the time you have spent with this interview is very valuable for your life. And I would like to invite you to stay tuned to the series of interviews conducted by Department of Chemistry, University of Colombo, as we plan on bringing the successful stories of many more eminent scientists to inspire you. Have a great day.